Everybody loves this video. I love the video too. Let me just show you the video really quick. This is on TikTok. It's really popular. Really popular. Play this. So it's a cop going down a slide in Boston, and he ends up going too fast, way too fast. And I mean, he was injured, but not severely. So, it's a great example of physics, like a real physics problem you'd find in an introductory physics course, but it's also in the real world, and so it's perfect for us to do it as a physics question. So number one, how fast was he going at the bottom? Number two, can we estimate the coefficient of friction between him and the other person? One of the things that people say, well, and I'm going to show you why this doesn't work. It's because it's a grown man going down the slide. He ended up going so much faster than a child. It's probably that vest he was wearing, right? Or something like that reduced the friction and made him go so fast. But let's just analyze it. So the first thing I want to do is, how fast was he going? Let's look at this from a video analysis perspective. It's not a great video for that, but we can do it anyway. I've already loaded this into Tracker Video Analysis. Here I have Tracker Video Analysis, my favorite video analysis program. And normally what I would do is to mark the location of him in each frame and get position versus time data so I could find a slope or something like that. But you can't do that here because he's moving towards the camera and not side to side. But let's just get the time. So I want to get the time it takes him to go from right here coming out of the slide to the end of the slide. And then if I know that distance and the time, I can get an average velocity. It'll be a rough approximation. So let's do that. Scrolling forward until so he's right. Is that him in the slide? I can't tell. Okay, go forward, forward, forward. There he is. He's halfway. Okay, let's set that as the first frame. So 141. And I'm going to mark that time. I don't really care about the position. I just need the time. So I'm going to just click there. It doesn't really matter where you click. Now I'm going to scoot down here. You could probably do something like measuring the angular size and stuff like that, but it's not a great video for that. And I used his middle point. So when his middle crosses right there, I get that. So I have a time interval of 0.833 seconds. I'm going to need that. I'm going to go ahead and write that down before I forget. So I'm going to do my calculations over here in not Google, in Python. So let's just go, dt is 0.833 seconds. We're going to need that. Now I need the position, the change in position, dx, right? How far did it go? So for that, I can go to Google Maps. Here, yeah, this is it in Google Maps. It's actually labeled cop slide, which is really great. Thank you, whoever did that. It's kind of funny too. Here's the slide. You can see it from the top. There is a 3D view that's kind of useful too. That's kind of cool. And it only really has one bend in it, but I want to get the distance from here down to the bottom. And it is at an angle. So if you look at it from the 2D perspective, this distance is not the actual distance, but it's just an approximation anyway. So let's just measure that distance. You can measure distances in Google Maps. Right click, measure distance. There's my point. I'm going to measure from here down to there, and I get 5.2 meters. So let's do that. dx 5.2 meters, and now I can calculate the average velocity. V average is just going to be dx divided by dt, and let's print that. V average equals V average meters per second. If you want to convert that, go ahead. I'm going to leave it right there. So 6.2 meters per second. Now, I'm going to calculate the coefficient of friction, but let's first calculate the maximum speed if there was no friction, how fast it'd be going. Because if this is greater than the maximum speed, then we're in trouble, right? Now, if I ignore friction, all I need is the height. How far did he fall? It doesn't matter if he's going down the slide or dropping. It's the same speed. But I don't know the height from the map. What I want to do instead is to get the length of the slide as seen from the top and the angle of the slide, which I can get from another picture. So let's first get the length. So over here, I'm going to go from, I'm not going to use I'm going to move this right there, right? This part right here is flat, so I don't really count that part. This I'm going to move up here to the bend. So that's at 9.28 meters. Let's write that down. I'm going to call that L1. L1 equals 9.28. Now the other length for the rest of the part is about, that's about like that. Because it curves, I'm just approximating, and I get 4.38. So let's call it L2. L2 equals 4. What did I say? 38. And that will be the horizontal distance, really, because I'm looking at it from the top, right? That's my horizontal projection of the slide distance, L1 plus L2. Now, what I need is the angle. It happens to be that there is a better picture of this that I found right here in this announcement of the video. Here's a picture. Let's open that in a new window. Open it. Open in new tab. And there you can see the side view of the slide right there. And you can load this into Tracker Video Analysis and get an angle measurement, which I did, and I got about 30 degrees. I'm not going to do that. I'm just going to say theta is 30 degrees, if that's okay. So theta is 30 times pi over 180. I need it in degrees. Now let's calculate how fast you'd be going with no friction. Jumping over to the paper. So here is my idealized slide. We'll come back to that again. Theta. And I have this distance Lx, that's Ly, and that's the total length L. I know theta, I know Lx, that's what I measured. So I can find Ly. Tangent of theta is opposite over hypotenuse, so that would be Ly over Lx. If I solve that for Ly, I get Ly is Lx tangent of theta. And I'm going to need that for the next part. Let's put y is equal to 0 down here. Since I don't care about the time, I only care about the speed, I'll assume that he starts from rest up here, and I want to find the speed down here at the bottom. I'll call that V2. This should scream out, use work energy. Work on the system is the change in energy. And I need to pick my system. I'm going to say it's going to be the cop, or law enforcement officer if you prefer, plus the Earth. And by adding the Earth in there, then I will have a gravitational potential energy. If you just have the cop, you have to do the work done by gravity. I don't want to do that. That means I have two types of energy. I have the kinetic energy of the person, 1/2 mv squared, and the potential energy mgy. So here, they're going to end up at y equals 0, start at y equals Ly. There is another force on the person, the normal force, but the person's moving perpendicular to the normal force. So the work done by the normal force is 0. We don't have to worry about that. So the work is going to be the change in kinetic energy plus the change in gravitational potential energy. 0 is K2 minus K1 plus U2 minus U1. And so it is always a change in energy here. So it doesn't really matter where you pick your y is equal to 0. Now, I do have a couple terms that are 0. If he starts from rest, if the V1 is 0, then K1 is 0. And if I put this as my final position, then Y2 is 0, so U2 is 0. So I get 0, 1/2 mv2 squared minus mgy1, which is going to be Ly. And the mass cancels, and I can solve this for V2 as the square root of 2gy1. So let's plug that in our calculator and see what we get for the value there. Switching back to the computer, let's calculate Ly. Ly is going to be equal to the Lx times tangent of theta. You can print that if you want to, but it doesn't really matter. And I do want to calculate V2 is going to be, this is called V2 max. This is the maximum velocity. Oh, I need G. G equals 9.8. I'm leaving off the units because they're just a comment. V2 max is square root of 2 times G times Ly. And print that, not parent, print V2 max equals V2 max meters per second. And let's see what we get. Please be greater. Okay, so that's good. It's a lot greater. Now, we need to find the coefficient of friction. I'm going to, because if there's a frictional force, he's going to slow down. What I can do is to get an expression for the acceleration and then actually find the acceleration based on that actual velocity at the end, which is the 6.24. And then set those equal to each other. So let's find a relationship between the acceleration of the person and the coefficient of friction. And let's go back to the paper. So again, I have my idealized slide. Like that. At some angle theta. There are three forces acting on the person. There is the downward gravitational force, mg. There's the normal force, n. And then if he's sliding down this way, there's a frictional force this way. And I should have had the slide in the other direction, but it doesn't really matter. Let's call this the x direction and that the y direction. So if you have a problem like this, it's going to help you out. We're using Newton's second law, F net equals ma. And if I want to break that into components, it's going to help if one of those components has an acceleration of 0. So in this case, I'm picking my y direction this way because the person's not going to accelerate that way, and that will make that component equal to 0. And then the acceleration in the x direction is the total acceleration, and that's what I want. Now there is one trick here. This angle is, I'm going to need that because gravity is in both the x and the y direction. And it turns out that that angle is the same as theta. You can do the geometry if you want. There's a lot of ways to do it. I like this way. This is 90 degrees, so that's the complement of theta. This is 90 degrees, so that's the complement of the complement, so also equal to theta. Now I can write down my net force in the y direction. F net in the y direction is going to be equal to the normal force minus this component of the gravitational force right here. So if I draw that, there's mg, and it looks like this, that's theta. This is my y component. So if that's mg, the y component is going to be the adjacent side. That's mg cosine theta. And since the acceleration is 0, that has to be equal to 0. And I can use this to solve for n, which is what I want. And I need that because this frictional force, the magnitude of the frictional force is equal to the coefficient of kinetic friction force times the normal force. That's the model that we're going to need. So I need that expression for the normal force, and that gives this coefficient of kinetic friction, mu, mg cosine theta. Now let's look at the x direction, F net x. And again, this is my positive x direction. Now I have, this is my component of the gravitational force in the x direction, and that's the opposite side of that angle. So this will be mg sine of theta. And the frictional force is in the negative x direction minus ff equals ma. I can plug in my value for the frictional force from right here. Mg sine theta minus mu k mg cosine theta equals ma. Notice something awesomely important here. Mass, mass, mass. The mass cancels. So it doesn't matter if it is a full-grown adult or a child. The mass, they should have the same speed. It does depend on the coefficient of friction, though. Cancel, cancel, cancel. I get an expression for A. A is G sine theta minus mu k, the coefficient of friction, g cosine theta. And you'll notice that if the coefficient of friction is 0, that term drops out. I get g sine theta, which is the acceleration of a block down a frictionless plane, so that's nice. Now we need an expression for the acceleration going down the plane. So here is my triangle. Look, I'm tracing it. It's exactly the same, theta. Now, in this case, I know the total length L, where I can find that. V1 is up here, 0. V2 down here. And I calculated that from the video analysis. You could use a bunch of different kinematic equations and find an expression for the final velocity and the acceleration. But I assume that you've seen the kinematic equations before. You know, we have this one, I'll call it x. X2 equals x1 plus v1 xt plus 1/2 a xt squared. But that has time in it. I don't want to use that. There's v2x equals v1x plus axt. Again, time. I don't want to use that. There is another one. You can solve these. I'm not going to do it because it's so common. v2 squared, v1 squared, plus 2a delta x. Now, this is the one I want to use. In this case, I know my length, delta x is L. I know v1 is 0, and I know v2, I got that. So I can solve this for a. So if that's 0, and this is going to be equal to 2al, I can solve for a. A is going to be equal to v2 squared over 2l. And just notice that's meters squared per second squared divided by meters does give me the right units for the acceleration. If I put that together with my other version, I had this. A is g sine theta minus mu k g cosine theta. Set that equal to this. I can solve this for mu k. I'm just going to solve this for mu k since I have an expression right there. So mu sub k g cosine theta equals g sine theta minus a, right? Because if I add this to both sides and subtract that, now I'm going to divide by this. I get the coefficient of friction is g sine theta minus a over g cosine theta. So that's my a that goes in there. G I know, theta I know, g I know, theta I know. And you'll notice that this has units of meters per second squared, meters per second squared, meters per second squared. So this is a unitless quantity. That's good. If there's no friction, then a would be g sine theta, and we'd get a 0 coefficient, which we just said. Duh. Okay. But now we can go ahead and calculate this coefficient of friction, right? Because I know the final velocity. I can calculate L. I guess I should say that. L, I know Lx. Lx is L cosine theta. So L is Lx over cosine theta. That's how I'll find that. I know 2. I got that. So let's do it. Calculate the coefficient of friction. Okay. Switching back to Python. And here's something that we have nice with Python is I don't need to substitute that in. It'd make it a little messy. I just need that as a number. So I don't have to simplify it all the way. V average is what I'm calling it. I should call that V2. Let's call it V2 just to make it look like my calculations. Oh, and then I need to change this to V2 or it's going to get mad. And I need to calculate L. It's Lx divided by cosine theta. You can't see that. A little bit off. Now I'm going to calculate the acceleration. A is equal to V2 squared divided by 2 times L. And now I can calculate mu. Mu k is parentheses g times sine theta minus a divided by g times cosine theta. And let's print that. print mu k equals mu k, and run it. 0.43. So, I mean, not super low. I calculated this before. It's a little bit lower, but it depends on your initial values. And there you go. Now, if you want to say, is that a reasonable value for the coefficient of friction? What's a good value? I mean, I don't really have a good value for that. If you want for homework, we can redo the problem right now. What if mu is 0.6? What would his final speed be? Let's do that real quick. So I just need to start with the final equation. I have a, I'm going to use this calculator. I'm going to just type, I already have the equation listed. So mu2 is going to be 0.6. A equals g times sine theta minus mu2 times g times cosine theta. Right, that was the equation I had, and I just want to print that out. So print nu A equals A meters per second squared. And I get a negative number. That's weird. Oh, I guess that's too high. He wouldn't even slide down. Let's just try 0.5. Okay, so a lot slower, right? Essentially going at a constant speed probably in that case. So if you just get a little bit, I feel like there's a problem with the calculation. Because I did this before and I got 0.3, which I was more happy with. If I did use a different distance here, dx. Let's just change this to 4.8. Because I didn't make the approximation that I did the length as constant, not angled. Well, that's weird. G sine theta minus A divided by, G cosine theta. Is that right? Okay, well, I'm going to go with it. And then A is V squared over 2L. Okay, well, that's how you do it. I feel like there's still an error, but that's fine. I'll make sure to put a link to the TikTok down below in case you want to play with that. And that's that.